In this lesson, we're going to talk about composition of functions. The expression f of g of x means f of g of x. This means that we use the output of the function g as the input of the function f. Okay, so imagine f of x is 2x minus 1 and g of x is root x. Let's get an expression for f of g of x and an expression for g of f of x. Well, let's go back to our first day learning function notation. We learned that if f of x is equal to 2x minus 1, then f of block must be 2 times block minus 1. Well, what if I say f of g of x? Then that would mean 2 times g of x minus 1. But what is g of x? G of x is root x. So that'd be like saying 2 times root x minus 1. So f of g of x must be equal to 2 times root x minus 1. Well, how about g of f of x? Well, again, day one of function notation, we learned that if g of x is root x, then g at block is root block. Well, what if the block is f of x? What if it's g of f of x? Then that would be the square root of f of x. What does f of x equal? Right there, f of x is 2x minus 1. So g of f of x would be the square root of 2x minus 1. Okay, and here is it shown in a more easy to read manner. We work from the inside out, so we see this g of x right there. We plug in what g of x is, and then we use our function notation principles. We see f of x here, we plug in what f of x is, and then we use our function notation principles. So we have an expression for both f of g of x and g of f of x. Now method 2 asks us to figure out f of g of 25 and g of f of 25. Well, we have an expression for f of g of x, so finding out f of g of 25 is just a matter of plugging in 25 for the x in that expression. So instead of saying 2 root x minus 1, we say 2 root 25 minus 1. Well, root of 25 is 5, so 2 times 5 minus 1 is 9. So f of g of 25 is 9. How about g of f of 25? Well, we know that g of f of x is the square root of 2x minus 1. So g of f of 25 is the square root of 2 times 25 minus 1. In other words, the square root of 50 minus 1, which is the square root of 49, which is 7. So notice that f of g of x does not equal, notice that f of g of 25 does not equal g at f of 25. Now that's method 1. You can use that method when you already have an expression for f of g of x. If you already have an expression for f of g of x and you want to know f of g of 25, you just plug it straight in. But what if in method 2 you don't actually have an expression for f of g of x? In that case, if you wanted to know f of g of 25, it might be a tad quicker to just, again, imagining in here they're looking for f of g of 25. If you didn't already have an expression for f of g of x, we can determine what g at 25 is and then plug that into f of x. G at 25 is 5, f at 5 is 9. Similarly, if we wanted to know g of f of 25, then it might be quicker in some cases to just figure out what f at 25 is. In this case, f at 25 is 49, and then determine what g at 49 is, which is 7. Both methods are correct. Now, suppose we have a couple of functions given as shown, and we want to determine all of these expressions, all of these values. Well, we could start by determining by stating, since we're looking for f at g of 7, we could say that that's equal to f of g of 7. Now you might say, well, what the heck is g at 7? Well, g at 7, if you recall from function notation, is the y coordinate that goes with an x value of 7 in the function g. G at 7 is 9. So that's like saying f at 9. Well, f at 9 is negative 3. because -3 is the y-coordinate that goes with an x-coordinate of 9 in the function f. How about g of f of 4? Well, let's figure out what f of 4 is. F of 4 appears to me to be 11. So now let's figure out what g at -11 is. I said 11, I meant -11. What's g at -11? G at -11 is 5. Bing. Let's do f of g at -3. Well, working from the inside out, we see g at -3 is 6. Good enough. Now, I want to now know what f at 6 is. Well, that doesn't exist. The reason it doesn't exist is there's no point in the function f with an x-coordinate of 6. And f of 9, well, that working from the inside out, we see that f at 9 is -3. Okay, so we then determine what f at -3 is, and f at -3 is 2. Now, what if we're given graphs instead? Let's try these. We want f at g of 4. Well, g at 4 must be equal to -1 because the point 4, -1 is in g. Alrighty, that's cool. Then that means I'm looking for f at -1. F at -1 must be 3 because the point -1, 3 is in f. What if I am doing part B? I want to know g of f of -1. Well, f at -1 is 3 because the point -1, 3 is right there on f. And then that means I'm looking for g at 3. Well, g at 3 is -4 because the point 3, -4 is on y equals f of x. There should be a negative in front of that 4. Okay? How about if we're looking for g of f of 1? Well, f at 1 is 5 because the point 1, 5 is right there on f. So g of f at 1 means g at 5, but g at 5 doesn't exist because the function doesn't go that far to the right. And if I want to know, finally, part D, if I want to know g at 3, I can say, well, g at 3 is -4. But, so therefore g at 3 is g at -4, but that doesn't exist because the function doesn't go that far to the left. And that is the end of the slideshow.